Hello everyone, we're going to go ahead and go over section 3.5, which is going to be on complex zeros and the fundamental theorem of algebra. So like we said in our last section, section 3.3, we're kind of going from graphing polynomial functions into more of the algebraic side. So we're going to continue on into this kind of algebraic side, and then we're going to mostly mesh everything together in the next sections. But still working with a little bit more of that algebra first here. So complex zeros and the fundamental theorem of algebra. So what we didn't explicitly quite state in our last section, but we have said before, was that for an nth degree polynomial, you can have at most n real numbered zeros. So for a polynomial of degree 4, meaning that the leading term would be x to the power of 4, you can have at most 4 real numbered zeros. But we don't always see that happen. A lot of time we can have maybe just 2 or maybe even just 1 because the other numbers aren't real numbers. That's kind of where this section is going to come into. So that's that idea there. You can't solve for x for the other values. Say, if you're going to take a square root of a negative number, we would have just said, okay, those zeros don't exist. But so for an nth degree polynomial, so for a polynomial of some degree, you can have at most that number of degree of zeros. So that's that idea that we've been working with so far. But with the complex number system, which is what we're introducing in this section, you will have exactly that many zeros because you can now do things like take the square root of a negative number. So that's really what the complex system is. It introduces the imaginary number I. So the imaginary number I is the square root of -1. So anytime you have a square root of a negative number, you can separate that into the square root of that number times the square root of -1, which is just I. So really the only complex number is the imaginary number, which is I, the square root of -1. Because really it's just multiplying I by some other number that would make it complex or imaginary. So it's a complex number. It allows us to take the square root of any negative number. Also, since I is equal to negative, or the square root of -1, that also means that I squared is -1. So we can see that there as well. But so this is what's going to allow us to have exactly the number of zeros as the degree of our polynomial, because we are now introducing the fact that we can take the square root of a negative number. Now, we can do this, but we are only doing this in this section. In no section in the future are you going to be taking square roots of negative numbers, and in no section in the past are you going to take square roots of negative numbers. It's really just this section where we do focus on taking square roots of negative numbers, and this section alone. There's really no other section where we necessarily do this very often. So we want to make that very clear that imaginary numbers only exist in section 3.5. So moving on, we had the fundamental theorem of algebra and this idea of complete factorization. So starting with the fundamental theorem of algebra, we say that every polynomial, which is p of x is equal to a sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1, adding all of these terms until you get down to a sub 1 times x plus a sub 0, where we say that n has to be greater than or equal to 1 and a sub n never equals 0. So every polynomial in this just typical polynomial fashion, like how you would see them anytime you'd see them. If it has a complex coefficient, meaning that one of these a sub n's or a sub n minus 1s or a sub 1s, any of these coefficients, if they have a complex coefficient, meaning that it has I in it. That's the only thing that makes numbers complex, is the introduction of an imaginary number. So if you had I in any one of these coefficients, that means that your polynomial has to have at least one complex zero, meaning that one of those values of your zero has to have an I in it. So that's really all we're stating here, is that if you have a coefficient that has I, one of your zeros has to have an I as well. That's the only way it could get there. So the only way that you result in an imaginary number is having an imaginary number to begin with. You can't just create an imaginary number out of nothing. It has to kind of start there if you have a value. So really that's all we're really stating here with this theorem of algebra. So then we have complete factorization of polynomials. So this is something that we're going to use like quite a few times. So our complete factorization of polynomials. If p of x is a polynomial with degree of n greater than or equal to 1, then there exists some complex numbers a, c sub 1, c sub 2, all the way up to c sub n, with a not being equal to 0, such that your polynomial is equal to a times x minus c sub 1 times x minus c sub 2, all the way until you get to x minus c sub n. So the complete factorization means that your polynomial can be 100% factored into these polynomials here of degree 1 that look like x plus or minus a number. And when you multiply out your polynomial, or you expand your polynomial into the multiplication of the different factors, they don't always necessarily have to be complex, but they may have complex values if your polynomial had to have had complex zeros. So we're just saying that the complete factorization of polynomials is the fact that you can express a polynomial in every single one of these factors. There's really no change, like no difference. They will all look like x plus or minus a number. That is how you have the complete factorization of a polynomial. You break it down into these factors that look like x plus or minus a number. That number may or may not be complex, so they may or may not have a value of I, but your polynomial will be broken down into all of these terms. So that's the complete factorization of a polynomial. So these theorems, they just tell us that complex numbers exist in the factorization of polynomials that we've already seen. So every type of, formula method that we have for factoring polynomials is going to be the exact same as before. It's just that now we're saying that complex numbers can exist as well. So we're kind of introducing this idea, but remember the format and the way that we solve them are going to be the same. So since they're going to be the same, you'll see some of these problems are going to be a little bit more on the challenging side, since you kind of already had practice at doing this, and now we're just introducing I, so they're kind of making the problems a little bit harder along with introducing I. So that's what you'll see in some of these problems, like example 1. So example 1, we're going to find all the zeros and the complete factorization of p of x, where p of x is equal to x to the power of 3 minus 2x plus 4. So we're going to find all of the zeros, complex and real, and we're going to find the complete factorization of our polynomial, meaning that we are going to take this polynomial that we're looking at right here, and we're going to expand it into terms that look like x plus or minus a number. Since this is a polynomial of degree 3, that means that we're going to have 3 zeros, which also means that we are going to have 3 factors, meaning that we're going to have 3 of those x plus or minus a number, x plus or minus a number, x plus or minus a number. So that being said, let's go ahead and go over to our notes to begin working on this problem. Alright, so here we are in our notes. We'll find the zeros and the complete factorization of our polynomial, which is x to the power of 3 minus 2x plus 4. So we want to do this, and we're looking at this problem, and we can think to ourselves, I don't really know where to start. I know what I'm supposed to do, but how do I really begin? And where we're going to begin whenever you are just kind of given this task to find zeros and complete factorization of a polynomial that is really going to be bigger than degree 2, since if it's bigger, or if it is degree 2, we can do things like using the quadratic formula and things like that. If it's bigger than degree 2, we can kind of feel a little bit stuck. But one thing which is a good place to start is that if you can find just one zero, then you can use synthetic division or long division if you'd like. And this is to find the remaining factor or factors. You will use this to find the remaining factors, but to begin with, you're just going to find that one polynomial that when it's multiplied by x minus that zero, that you kind of get that result. So if you can just find one zero, you're kind of good to go from there, because you can use synthetic division, you can break it down further, and then further and further until you get to kind of where you need to stop, which is the complete factorization of the polynomial. But knowing when to start is kind of hard and can be pretty difficult. One way that you could try to find one of these zeros is by plugging and chugging. And that is not quite an excellent way of checking, because you could be checking a lot of numbers and it could take a really long time. You could make it a little bit more strategic than not. If you look, you can find the final value in your polynomial. So in ours, it's 4 because that's the last number of the polynomial. And you could try out every single number that is a factor of 4. And that way you can find a zero if you can. So this is going to be 1, 4, 2, -1, -4, and -2. So that's, like 6 or 7 factors right there, 6, 7 numbers. Just to begin with, that you would have to be plugging into the polynomial to check. And I mean, luckily for us, 4 isn't that big of a number. So you could be plugging in numbers that are much, much larger. If you have something like 24, you would be plugging in a lot of numbers into this polynomial. It could just kind of get very ridiculous if you don't have kind of a simple value, a smaller value like 4. But even thinking about the number 4 is quite a few values there that you're going to have to be plugging into your polynomial. And so plugging in values and like plugging and chugging to see if it's a zero, because remember, if it's a zero, the value will be 0. So when you plug in that number, it will come out to 0. Instead of doing things like that, a really great way of checking or finding a zero is graphing. So we're going to go ahead, we're going to go to Desmos, we're going to graph this function, and we're going to look for that 0. All right, so here we are in Desmos. We have our function graphed, x cubed minus 2x plus 4. And what we're looking for is that we know that when we plug in some x value into our function, it should equal 0. That means that x is a number and y is 0. If we put that into an ordered pair, that would be some number, comma, 0, which is the same thing as an x-intercept. So if you ever want to find a 0, especially for problems like these where complex numbers are going to be zeros, because complex numbers do not show up on graphs, for one. Your coordinate plane only shows real numbered zeros. It does not show complex zeros. So in cases like this where you are inevitably going to have complex zeros, but you need to know at least one real numbered 0 to help you with synthetic division and things like that, and kind of breaking down that polynomial, graphing is a great choice to just find one, because a 0 is the same thing as the x-intercept. So in our function right here, we want to look for that x-intercept, and it's right there. It is -2, 0, which means that -2 is a 0 of our polynomial. So we're going to go ahead, we're going to go back to our notes, we're going to write this out, and then we're going to continue on with our problem. All right, so back to our problem, -2, 0 is the x-intercept for our polynomial, so -2 is a 0 of our polynomial. And as a reminder, we got that from Desmos. So we just saw that, we graphed the function, we found the x-intercept, so that means that -2 has to be a 0. So now we can use the value of -2 to go ahead and do synthetic division or long division. So since -2 is a 0, this means that x minus -2, which is the same thing as x plus 2, is a factor, and c would be equal to -2 as well, because remember c is 0 or the 0. So x plus 2 is a factor. This also means that c is equal to -2. So now we can go ahead and do synthetic division. So when we set up our synthetic division, we have our upside down house, we have c on the outside, and then we write the coefficients of all of our x terms from our polynomial with the dividend inside that house. So when we write out our synthetic division, we're going to have -2, upside down house. And looking at our polynomial, we have x to the power of 3 minus 2x plus 4. If we were to write this out, this is really, 1x to the power of 3 plus 0x squared minus 2x plus 4. So the coefficient of x cubed is going to be 1. Since we don't have an x squared term, that coefficient is 0. The coefficient of x is -2. And that last number is 4. So there we go. Kind of set up our synthetic division. We draw another line here to represent our middle row, and now we can start our synthetic division. So as before, we say we copy down the first term. I'm going to use a different color for that one actually. We copy down that first term, so that first number just goes straight down to the bottom row. And then we multiply the value of c to that number in the bottom row. So we multiply. And then we write our result in the middle. So -2 times 1 is -2. Then we add the column. And 0 plus -2 is just -2. And we do the same thing again. -2 times -2 is going to be 4. Then we add -2 plus 4 is going to be 2. Then we multiply -2 by 2, write our results up here. -2 times 2 is -4. We add the column, and that comes out to 0. And there we go. So we finished up our synthetic division. We want to remember that this number right here is the remainder. And this part here is our quotient, or really what we're looking for, it's our answer. And remember, starting from the right, you're going to go to the left, and you're going to add on x, and with increasing exponents by 1, starting at 0. So we add x to the power of 0, x to the power of 1, x to the power of 2. So our quotient in this case is going to be x squared minus 2x plus 2. That's our quotient. But a big part of what this means is that this is also the other factor. This is our other factor of p of x, which means that at this point that we're looking at right now, p of x is equal to x plus 2, because this is x, minus c, where c we said was -2. So x plus 2 times x squared minus 2x plus 2. So our first step in factoring p of x was finding that 0 and then dividing our polynomial by that 0, or the factor that corresponds with that 0, so that we can find the other factor. So we're doing pretty well so far. We've got p of x is equal to x plus 2 times x squared minus 2x plus 2, but this is not the complete factorization. In complete factorization, every single factor has to look like this first one. They all have to look like x plus or minus a number, and that is not what x squared minus 2x plus 2 looks like. So we need to break down this factor up into smaller factors. So for example, it would need to be x, minus c sub 1 times x minus c sub 2. This is what we're looking for right now. So we need to break that up into smaller factors to get the complete factorization. So this is a quadratic function. We learned about, how to solve these, how to factor these back in section, like 3.1. So we need to factor this, and the way that we're going to do it, because we can try to think of all, the different ways to factor. We can like backwards foiling, two numbers that multiply to a positive 2, that add up to a negative 2. And whatever method you use, you will inevitably find that you can't factor it. And this is because it requires a complex number, a complex zero. And the only way you're going to find that is by using the quadratic formula. So we need to break this factor up into smaller factors by using the quadratic formula. So that's the only way you're going to solve and find those smaller factors. So we're going to scooch down a little bit here. And now we're going to use, or we're going to find the quadratic formula. We're going to find the factors by using the quadratic formula. There we go. So from this statement here, the quadratic formula you want to remember is x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. That is the formula for the quadratic formula. Yeah. So we use these a, b, and c values from our given quadratic function. So in our case, we've got ax squared minus bx plus c. So for us, we have that a is 1, b is, oh, that should be a plus there. Sorry about that. So b would be negative 2 in this case, and c would be positive 2. So it should look like a x squared plus bx plus c. So that's how we get our values of a, b, and c. And now we're going to plug these values of a, b, and c into our quadratic formula to find x, where x are zeros. So let's write that in real quick. Right here, these are zeros. All right. So we're going to find these values. So b, we said, was negative 2, so this will be negative negative 2, plus or minus the square root of negative 2 squared minus 4 times 1 times 2. This is all divided by 2 times a, which is just 2 times 1. So we're going to simplify this. Go to the next line here. Negative negative 2 is just like a double negative there, so it's really positive. So we've got 2 plus or minus the square root, and negative 2 squared is 4. And 4 times 1 is 4, times 2 is 8. So we've got the square root of 4 minus 8 divided by 2. 2 times 1 is 2. All right, well, let's simplify this a little bit more. 2 plus or minus 4 minus 8 is negative 4. And up until this section, we would have seen this and gone, oh, we don't have zeros. I need to take the square root of a negative number, and I can't do that. In this section, you can. So that is the idea with this section. So we see that this problem has been fairly difficult so far, and this is what I was trying to explain a little earlier on. The fact that we now have these complex zeros come from the fact that we're about to find the value of the square root of negative 4. But that really wasn't until this part of the problem. So these problems are inherently a little bit more difficult than the last section that we saw, or last few sections that we've seen, just because you've been doing this. So they imagine that you're kind of good at this already. So they made the problems a little bit harder now. So that's kind of the idea here. But the main point of the section is what we're about to do. So square root of -4, we're just going to grab that. We're going to take this whole statement, bring it over here. Square root of -4. We're going to separate this because we said that the complex numbers is really just the imaginary number I times regular real numbers. So I, remember, is the square root of -1. And whenever you have a square root and you have multiplication underneath the square root, you can separate those things. So starting off, we can just say this is the same thing as saying the square root of -1 times 4. This is -4. That's -1 times 4. And then we can separate the square root into 2 square roots. You can do that whenever you have multiplication or division underneath square roots. So this, and we're going to put this on the next line actually, this is the same thing as the square root of -1 times the square root of 4. Well, we said the square root of -1 is I, the imaginary number. And the square root of 4 is, well, plus or minus 2. So really this is plus or minus 2 times I, which is just plus or minus 2I. And that's the answer. That's the complex number. So we're going to plug that in and we're going to replace the square root of -4 with that. So coming down here, we're going to have 2 plus, since we already have this plus or minus in front of the square root of -4, we don't need to write it twice. It means the same thing. So we're just going to have 2 plus or minus 2I divided by 2. And we see in this case, there's a 2 in every term. So we're going to cancel out the 2 in every term. And what was left over was 1 plus or minus 1I. And we'll highlight this one. So we have 1 plus or minus 1I. You don't even necessarily have to put the 1 in front of the I if you don't want to. You can just write 1 plus or minus I. And those are 2 more of our zeros because remember, whenever you have this plus or minus, it means one of each. So this is really 1 plus I and 1 minus I. So it's really both of these statements here. I'm going to spread that out. I'm going to write the word and so it doesn't look like an ordered pair. Come on. There we go. So it's really both of these values. So now what we've established at this point is our zeros are -2, 1 plus I, and 1 minus I, which is part of what we want to define. We want to define the zeros and the complete factorization of our polynomial. So by breaking down that quadratic function and finding the zeros of it using the complex number, really just I, we went ahead and we found the remaining 2 zeros. Because this right here was a 0. 0 was -2. These are more zeros. So these were the 2 remaining zeros. So those were the 2 remaining zeros, which means that all 3 are -2, 1 plus I, and 1 minus I. So for the very last part of our problem, which was asking for the complete factorization of p of x, we're going to plug all of these in. So remember, the complete factorization of p of x would be, in our case, since we have 3 zeros, we're going to have 3 factors. And we don't really want to forget, remember, in the complete factorization, we had this number in front of all of our factors as well, which in our case is just 1. So we've got 1 times x plus 2, because we had that from up here. And then we have our other two factors here. So this is like c sub 1, c sub 2, and c sub 3. So the complete factorization, if you forget, is that p of x would be equal to a times x minus c sub 1 times x minus c sub 2 times x minus c sub 3 for a problem like this, because there's 3 zeros, so there's 3 factors. So in our complete factorization, we're just going to grab those c sub 2 and c sub 3 and just kind of shove it into place. So, because we saw that's what happened right here, we took c sub 1, plugged it in there, it was x minus negative 2, so it came out to be plus. And now we're going to do that here as well. So we're going to have x minus c sub 2. C sub 2 is 1 plus I. And same thing for c sub 3. X minus c sub 3, which is 1 minus I. So we took c sub 2 and c sub 3 and just shoved them into place. And this would be the complete factorization of your polynomial. And if you wanted to simplify, you could definitely simplify by distributing that minus inside of your polynomial. But you don't have to. I believe WebAssign will accept an answer like this, and definitely an answer like this is completely acceptable on an exam. Or you could simplify, so say, or, p of x is x plus 2, and x minus 1 minus I, and x minus 1 plus I. So you could write it this way as well. Either way would be correct, either more simplified or a little less simplified. They are the same. Once again, I believe WebAssign takes both, and either one is completely okay on the exam. So, all right, that wraps up example 1. So let's go ahead and go back over to our notes. All right, so that wrapped up example 1. So let's move on. On zeros and their multiplicity. We say that a value of c is a 0, and it can have multiplicity k. And the multiplicity really stands for an exponent on a factor. So we're saying that if we have this value of 0, or this value of c, that's a 0, then its factor would be x minus c. And if x minus c had an exponent, that means that it would appear like k times, if the exponent was k, it would appear k times in the complete factorization of p of x. It would show up as many times as the exponent said. And that means that it would have multiplicity. And the multiplicity is really meaning the exponent. So, like as an example, if we say that p of x is some function x minus 1 cubed times x plus 2 squared times x plus 3 to the power of 5, like what we have in this polynomial here. This means that we really have 3 zeros. We have 1, negative 2, and negative 3. Because if we plug in any one of those numbers, it would make the whole thing 0. So we really only have 3 zeros. But our polynomial is going to have degree 10, because you see the exponents are 3, 2, and 5, so 3 plus 2 is 5, plus 5 is 10. So this would be a polynomial of degree 10, which means that we should really have 10 zeros. So that's where multiplicity comes in. We saw that x minus 1 had the exponent 3. So this factor here has multiplicity 3. The value, or the 0 of 1, would show up 3 times. We would write it 3 times. So that's why we have 1, 1, 1 listed here for the zeros. Then for negative 2, it has multiplicity 2 because the exponent was 2. So since it had multiplicity 2, we had to write it twice when listing our zeros. Then lastly, negative 3 would have multiplicity 5, so we need to list it 5 times when listing our zeros. So if you have an exponent on a factor, that is going to be attributed to multiplicity. The 0 is the 0, but how many times would you write it? That's the idea of multiplicity. So our zeros theorem is just the book's way of saying the same thing that we just talked about, but it says that every polynomial of degree n greater than 1, greater than or equal to 1, has exactly n zeros. So every polynomial of degree n will have exactly that degree number of zeros, provided that a zero of multiplicity k would be counted k times. We obviously saw in this example right here with p of x, we see that there were really only 3 zeros, but because of the multiplicity, there ended up being 10 zeros for our polynomial of degree 10. So you do count, if you have multiplicity on one of those factors, you would count it that many times as its exponent. So that's really what multiplicity means. So we're going to go ahead and do an example. So example 2 is we're going to find the complete factorization and all 5 zeros of polynomial p of x is equal to 3x to the power of 5 plus 24x cubed plus 48x. So, all right, we're going to go ahead and work on this example. All right, so here we are with our notes. Problem 2, we've got p of x is equal to 3x to the power of 5 plus 24x cubed plus 48x. Now remember, we're finding all of its zeros and writing its complete factorization. So the first thing we always want to do whenever we look at a polynomial is that we want to figure out right away, can I factor anything right off the bat? And the answer for us is going to be yes. We can factor a 3 and an x out of the whole polynomial. So instead, we can say p of x is equal to 3x times everything left over. So we're going to have x to the power of 4 plus 8x squared plus 16. So that's how p of x is going to factor. Then we also want to realize in this case that since we factored out an x, if x were 0, it would make the whole polynomial 0, which means that one of our zeros is x equals 0. So that's one of them right off the bat. So now we're only looking for 4 zeros because we said that our polynomial will have 5 zeros. So this really means that we're now looking at the rest of this portion right in here. We want to know, how are we going to factor x to the power of 4 plus 8x squared plus 16? How are we going to find the zeros? We actually can't use the quadratic formula because our highest power is 4. You can only use a quadratic formula if your highest power is 2. So we're looking at this and we want to realize I could factor that with any kind of typical factoring methods if that were x squared plus 8x plus 16. So we're just, for example, going to write that. So below it, we're going to say, all right, I've got x squared plus 8x plus 16, just as an example. I would factor this by thinking of two numbers that multiply to 16 and add to 8. And those two numbers would be 4. If I have x plus 4 times x plus 4, that's how x squared plus 8x plus 16 is going to factor. And for that matter, x plus 4 times x plus 4 is x plus 4 squared. So if I were to factor my polynomial in this way, that's what I would end up getting. But like we said before, our exponents are doubled. So we started off with x to the power of 4 plus 8x squared plus 16. And we found the answer if it were x squared plus 8x plus 16. So our two exponents on our two x values have doubled from 2 to 4 and 1 to 2. All this means is that in factorization of our polynomial, we would factor it the exact same way. It's just that instead of x plus 4 squared, we're going to have x squared plus 4, and all of that is squared. So if you have something that looks like the polynomial that we have, x to the power of 4 plus 8x squared plus 16, and if it looks like you could probably factor that using a typical factoring method, if the exponents were 2 and 1 instead of 4 and 2. Factor it the same way that you would always factor it and double the exponent on x. So while x squared plus 8x plus 16 factored into x plus 4 squared, x to the power of 4 plus 8x squared plus 16 factored into x squared plus 4 squared. So now that we've reached to this point, we want to realize the squared part on the outside is telling us that whatever zeros that we get from this, they're going to have multiplicity 2. So we need to identify what the zeros are. I'm going to bring this down a little bit. We can identify the zeros by taking x squared plus 4 and setting it equal to 0. And we're going to solve for x. So solving for x, we're going to subtract 4 from both sides. We get x squared is equal to -4. Only way to get rid of a square is to take a square root. So we'll take the square root of both sides. And we get x is equal to the square root of -4. And here we go. Here's our imaginary numbers coming in, because we see that we're now taking a square root of a negative number. If we were to take the square root of +4, we would end up getting plus or minus 2. But since 4 is negative, we add an I to our answer. The I is attributed to that negative part, or whatever your square root is. So the square root of +4 is plus or minus 2. So the square root of -4 is plus or minus 2i. So whenever you take a square root of a negative number, your answer is always going to have an I on it. So we have that x is equal to plus or minus 2i. We know that this means that x has 2 answers. -2i and +2i. There we go. So we've got those 2 answers. So far, our zeros are 0, -2i, and +2i. That's only 3 zeros. But remember, we count the ones that have multiplicity as many times as the exponent says. So because -2i and 2i originally had multiplicity 2, these zeros get counted twice. -2i and 2i both have multiplicity 2. So when we list out our zeros, we list them twice. So we're going to have -2i, -2i, 0, 2i, and 2i. So these are the zeros of our polynomial. And we counted that multiplicity. Now our last step was that we just want to make sure to do the complete factorization of our polynomial. So that's going to look like p of x is equal to, we've got 5 zeros, and so we're going to have 5 factors. We're going to write x minus, leave a space, 5 times. And we can't forget the coefficient of 3 from the beginning. We pulled out that 3 from the get-go. We have to put it back in the complete factorization of our polynomial. So we remembered the 3. We're going to write our 5 factors. We've got x minus, leave a space, 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 and x minus, leave a space. Just barely fit that in. So we're going to fill in with our zeros. Our first 2 being -2i. So we've got x minus 2i, or x minus -2i, which in this case is just going to be plus. Then we've got x minus 0,
x minus 2i, and once again, x minus 2i. So this would be the complete factorization of our polynomial. So we have the zeros and the complete factorization of it using multiplicity. So, all right, that wraps up our example 2. Let's go ahead and head back over to our slides. All right, so we wrapped up example 2. Now talking about another part here is going to be complex zeros that come in conjugate pairs. So what we just kind of saw before was that we worked with multiplicity and we saw something interesting. We saw that when we had a complex number, we really had two of them. We had the positive version and the negative version. And this is going to happen quite a bit. And we call these complex conjugates. So complex zeros of polynomials with real coefficients will always come in pairs. So you're looking at a plus bi. So if a plus bi is a 0, with a and b being some average number that you know, then its complex conjugate, a minus bi, is also a 0. So complex conjugates means that you have something that looks like a minus bi or a plus bi, and its opposite, meaning same thing but opposite sign, is called its complex conjugate. So if you're given a minus bi, its complex conjugate is a plus bi, and then the other way around as well. And they're always going to come in pairs. So if you get that one is a 0, the other one has to be a 0 as well, because they're always coming in pairs. So if you're told that some number like 3 plus 2i is a 0, 3 minus 2i has to be a 0 as well. They're always coming in those pairs. And it always comes from the fact that we have to take a square root. And when we do, we get the plus or minus version out of it. So the conjugate zeros theorem is the same thing as we just said. It's just the book definition. We say that if the polynomial p has real coefficients, and if the complex number z is a 0 of p, in this case, z would be like a plus bi, then its complex conjugate, which we call z bar, has a bar above the z, so it's called z bar original. But its complex conjugate, which in this case would be something like a minus bi, is also a 0. So it's the same thing as we said, just with book definitions instead. But all right, so complex conjugates come in pairs. So we're always going to see this. And this leads us into our next example. Example 3, we want to find a polynomial p of x of degree 3 that has integer coefficients and the zeros 1/2 and 3i. So let's go ahead and work on this example. All right, so here we are working on example 3. Now our problem told us that we want a polynomial of degree 3. It has to have integer coefficients and it has to have the zeros 1/2 and 3 minus i. Now, we wrote down some important formulas off to the side here. These are going to help us a lot during our problem. So I invite you to pause the video and write the important formulas down. But we're just going to talk through it really fast. So the difference of squares tells us that if we have something that looks like a squared minus b squared, it factors into a plus b times a minus b. Then we also have another unique thing called the sum of squares. The sum of squares only works when you have complex coefficients. So it's really, we're only using it for this section. We'll never use it again. So only for this section can you use the sum of squares. But this is actually where we get complex conjugates. The sum of squares tells us that if we have a squared plus b squared, that would factor into a plus bi times a minus bi. That's how we get the complex conjugates. Then we have lastly the perfect square. This is telling us that if we have x plus a squared, that expands into x squared plus 2ax plus a squared. Or if we have x minus a squared, that would expand into x squared minus 2ax plus a squared. we're going to use these, and they're very important to this section. We see that there's going to be a lot of times where we're going to have to expand and multiply certain factors together, and knowing these formulas are going to save us a lot of time. So especially if, say, you're going to be needing to do something like this in the near future, and you'd like to save a lot of time, these formulas are going to be incredibly important. They're, I would dare say, crucial to doing problems like these in a timely manner. You can definitely do them without using the formulas, but they take a lot of extra time, a lot of extra stress. So that's why we're going to use the formulas when we do this problem. But all right, so we know what we need to do. We know what we want. We know what type of polynomial we need to find. But first, let's remember, complex conjugates come in pairs. And we've been told that 3 minus I is a 0. This means that 3 plus I has to be a 0 as well. So here we go. Also, 3 plus I. And these are the complex, or this is the complex conjugate pair. So there's our complex conjugate pair. So we know that our polynomial has these 3 zeros. So we can go ahead and set up our polynomial in its complete factorization form. So we're going to have p of x is equal to some value of a. This is going to help us get integer coefficients in the end. So we'll kind of use this in the end, but it's just going to hang around until then. So we've got a times x minus, we'll leave a space, x minus, leave a bigger space, and x minus, leave another bigger space. We're going to put our zeros in the spaces. So our first 0 is 1/2. So we're going to have, x minus 1/2. Then we're going to have x minus 3 minus I. Since 3 minus I is an expression, we want to keep it in parentheses. Then our last one, x minus 3 plus I. So this is going to be the complete factorization of our polynomial. We're starting at the end, moving upwards. We're creating the polynomial. But what we just did there gave us a check mark on the zeros. We put all these zeros into their factors, so therefore our polynomial is now going to have these zeros. So what we're going to do now is we're going to do some rearranging. We see that, a and x minus 1/2, those are what they are. There's not really a whole lot to do with that. But this x minus 3i, like x minus 3 minus I and x minus 3 plus I, we're going to go ahead and get rid of those parentheses and see what we can kind of do with it. When we get rid of the parentheses, remember we're distributing the minus. So our polynomial will look like a times x minus 1/2. And now we're going to have x minus 3 plus I. We distributed that minus sign. We got a double negative. Then for the third one as well, we're going to have x minus 3 minus I. And the key for these problems is that we want to use the difference of squares. This one up here. This is what we want to use because we want to get rid of the I. We don't want to multiply these terms out and have a bunch of terms that have i's in them. We don't want to deal with it. So we're going to use the difference of squares so we can get rid of the I, because remember, I squared is -1. So what we're going to do is that now that we've distributed the minus, we're going to redraw some parentheses. And this is the key here. We're going to draw parentheses around x minus 3 because we can use the difference of squares by saying that x minus 3 is a. It's an expression, but it's still, going to work the same. Then I is going to be b. So these factors are a plus b and a minus b. Now we can use the difference of squares. And we just avoided multiplying a lot of things out. That's why we want to use these important formulas. We just avoided a whole lot of multiplication, a whole lot of time, a whole lot of energy. Nobody has time for that, okay? Just use the formula. We're going to use the formula and just go from there. So we're going to have a times x minus 1/2. We're going to put some bigger square brackets around this part just because we want to keep it just very separate, and too many parentheses gets too messy a lot of the time. So we've got a plus b times a minus b. And according to our difference of squares, that's going to simplify into a squared minus b squared. And a is x minus 3. So we've really got x minus 3 squared minus b squared. And b is I. So we've got x minus 3 squared minus I squared. And we've said this before, but I squared is equal to -1. So that number there is really just -1. Now we want to expand out x minus 3 squared. And this is where we're going to use the perfect square. So we want to use the perfect square right in here. Another reason why having these important formulas on hand is very important. And by on hand, I mean written on a note card. Be very helpful for you. So we're going to expand x minus 3 squared by using the perfect square. We're going to have a times x minus 1/2. And x minus 3 squared, we see that this value of a is 3. So we're going to have x squared minus 2 times a, so 2 times 3, which is 6. So minus 6x plus a squared, we said a is 3, so plus 9. So that's what x minus 3 squared factors into. Then we've got minus -1, since I squared was -1. And now we're just simplifying. We've got a times x minus 1/2, and really we're just adding a 1 to that longer polynomial there. So this is x squared minus 6x plus 10. And now that we have this statement, we still have to multiply. We're going to have to multiply x minus 1/2 and x squared minus 6x plus 10 together. So we're going to FOIL this. So we're going to move this down just a little bit here. Come on. There we go. And we're going to FOIL. Oh, whoa. I didn't even know I could do that. That was cool. All right. So we're going to FOIL these together. Now we actually have to multiply something. It's not going to fit in with any of our formulas, so it's not really going to work out. So we have to multiply them. But we see that we've kind of skipped multiplying things twice. And if we did multiply both of those out instead of using the formulas, it would have been a lot longer. And now we'd have to do it again. So by using the formulas, we got to skip it twice out of 3 times. So it's definitely worthwhile. All right, now we've got to multiply these terms together. And this is really using the FOIL method. It's not exactly FOIL since we've got one term that has, 3 terms in it, but same thing, it's the distributive property. So we're going to distribute x to every term in x squared minus 6x plus 10, and we're going to distribute -1/2 into every term in the x squared minus 6x plus 10. So starting off, we're multiplying x by x squared. So we've got a times x cubed, x times -6x. So this will be -6x squared, and x times 10. So plus 10x. Now we're going to distribute the negative 1/2. So we're going to have negative 1/2 times x squared. This gives us minus 1/2 x squared. Negative 1/2 times negative 6x gives us a plus 3x. And lastly, negative 1/2 times 10 gives us a minus 5. So we multiplied it out. It's looking good. But we want to realize something. One of the things that we wanted from the beginning was that we wanted integer coefficients. Integers are whole numbers that are positive and negative and include 0. So this means no fractions, no decimals, no square roots, no imaginary numbers. That's what we're dealing with here. And we already see that there's a fraction in our expression. There's a 1/2 x squared. We don't want there to be any fractions at all. So we could combine all of our terms as they are right now and then deal with the fraction. Or we can just deal with the fraction right now, and we don't have to deal with adding numbers to fractions. And that's a better choice. So we see right now, there's a fraction. I don't want a fraction. I want to pick the smallest positive value of a that I could possibly have in order to multiply to every single term in the statement that would get rid of that fraction. And that number is going to be 2. If we multiply every single value in this whole expression by 2, that fraction will go away. Doesn't matter what happens to all the rest of them. They're all going to get multiplied by 2, but that's fine as long as we got rid of the fraction. So we're going to say a is equal to 2. So we'll multiply 2 by every term in our expression here. We'll have 2x cubed minus 12x squared plus 20x minus 1x squared plus 6x minus 10. And now we can combine our terms without having to worry about fractions. So our last step to combine our terms here, we see that the x squared terms and the x terms can be combined. This gives us p of x is equal to 2x cubed minus 13x squared plus 26x minus 10. And that is our final polynomial. And we see, we just want to make sure that, hey, we've got integer coefficients. All of the coefficients are whole numbers that are positive or negative. And our polynomial is of degree 3, since the highest exponent in our polynomial is 3. So that's kind of how we would do a problem like this in this case. And in all honesty, you'll have quite a few problems like this on your homework. So it is more than worthwhile for you to copy down and have these important formulas on hand as you do these problems. It's really going to cut out a lot of time, energy, stress, and all that kind of stuff. To have those on hand and kind of know when to use them. All right, that wraps up our example 3. So let's go ahead and head back over to our slides. All right, that was example 3. Now our last thing we want to talk about is this idea of linear and quadratic factors. So what we've been doing so far is that we've been getting these complex numbered factors. And we've been saying that since a polynomial, if we're going to find its complex factors, we would factor our polynomial into the exact number of factors as its degree. But previous to this section, we wouldn't have factored all the way because we didn't really know imaginary numbers. And when we did that, we broke up our polynomial and factored it into linear and quadratic factors. So what's stated here is that a polynomial factors completely so 100% into linear factors, meaning x minus a number. They're linear because x is technically of power 1, and that's a line. So they're called linear factors when we use complex numbers. But if you work with real numbers, so not considering I, you would factor them into linear and or quadratic factors, meaning that they would be linear in the sense that they were x minus a number, and or quadratic factors, meaning you would have x squared factors. And typically, we would factor these with complex numbers, but we don't if we don't want complex numbers. That's kind of what we're saying here. So previous to section 3.5, we would have stopped at a quadratic factor that would have required us to take a square root of a negative number. This section, we allowed it, and next section, and for the rest of the semester, we're not going to allow it again. So that's kind of what we're saying here. And a quadratic factor, those ones with the x squareds in them, with no real zeros, meaning that your zeros would be complex numbers, they're called irreducible. So they're irreducible over the real numbers, which means that they cannot be factored without using complex numbers. So it's irreducible if when you solve it, it's got an imaginary number. That's what we're looking at. So in our theorem, we say our linear and quadratic factors theorem, every polynomial with real coefficients can be factored into the product of linear and irreducible quadratic factors with real coefficients. So every polynomial, if you're completely disregarding complex numbers, every polynomial would be factored into linear and irreducible quadratic factors. If you are factoring with complex numbers, you would factor them completely all into linear factors in that case. So we're kind of going to see in our next example what this means. It pretty much means that we're going to be asked to do both, completely factor our polynomial with complex numbers and compute them using linear and irreducible factors, which really just means that we're doing one problem, and like part A is the answer that's like 75% of the way through, and the answer for part B is the answer that's 100% of the way through. That's kind of what we're looking at. And you'll see that in a second here with example 4. So example 4 is let p of x be equal to x to the power of 4 the plus 2x squared minus 8. We're going to factor p into linear and irreducible quadratic factors with real coefficients. So basically no i's, no taking any square roots of negative numbers. And part B, we're going to factor p completely into linear factors with complex coefficients. So part B, we're just going to continue and use complex numbers. So all right, let's go ahead and go over to our notes to do this example. All right, so example 4, we've got this polynomial p of x is equal to x to the power of 4 plus 2x squared minus 8. We want to A, factor into linear and irreducible factors, and part B, we'll just factor it completely, pretty much like how we've been doing all section. So A, we want linear and irreducible factors. So looking at our polynomial, right away, we want to look for easy ways to factor our polynomial. Anything that we can take out, any type of like factoring, like method we can use, anything along those lines. And there is one. We're looking at this, we're thinking, x to the power of 4 plus 2x squared minus 8. My exponents have been doubled. And like we said earlier, if this were x squared plus 2x minus 8, I could factor this by figuring out the two numbers that multiply to negative 8 and add to 2. Well, that'd be x plus 4 times x minus 2. So, since our exponents got doubled, that means that in our factorization of p of x, we'll double the exponents on the factors. So x to the power 4 plus 2x squared minus 8 is going to factor into x squared plus 4 times x squared minus 2. So same factors, exponents get doubled. So if the exponent is doubled in the polynomial, the exponents are doubled in factorization. So we've got p of x is equal to x squared plus 4 times x squared minus 2. We can notice some things off the bat. One is the sum of squares, and the other is the difference of squares. So first, we're gonna focus on x squared minus 2. So looking at x squared minus 2, this is the difference of squares. 2 isn't exactly a square, but it was technically the square of the square root of 2 squared. Either way, you can set this factor equal to 0 and solve for x. So we say x squared minus 2 set equal to 0. We're going to solve for x. We're going to add 2 to both sides. We've got x squared is equal to 2. Only way to get rid of that square is going to be to take square root. And we get x is equal to plus or minus the square root of 2. Which means that our polynomial factors into x squared plus 2 times x minus, leave a space, x minus, leave a space. We found 2 zeros. So we're going to plug those in. X minus negative square root of 2. So those will be positives, plus. And x minus the square root of 2. So there we have it. But x squared plus 4, that's the sum of squares. And if you wrote it down, like you should have earlier, the sum of squares, we said factors into something that will contain I. And remember, if we only want linear and irreducible factors, no i's. We can't have any complex numbers. If we have to have a complex number, this automatically means that this is irreducible. So x squared plus 4 is an irreducible factor, because the only way to reduce it is to use complex numbers. So x squared plus 4 is irreducible. X squared, or x plus the square root of 2 and x minus the square root of 2 are linear factors. So what we have here is a polynomial with linear and irreducible factors. So this would be our answer for part A. Now, to do part B, all we're going to do is factor the x squared plus 4. Part B was that we wanted complex factors. So thinking of the sum of squares with x squared plus 4, we said that with x squared plus 4, using our sum of squares, this would turn into x plus 2i times x minus 2i. And that was using the sum of squares, remember. Then we still had x plus the square root of 2 and x minus the square root of 2. So this right here, sum of squares. That told us that if we had x squared plus a squared, this factored into x minus ai times x plus ai. Oh, I just barely squeezed that in. It's ugly though. But there we go. That's how we got the sum of squares. And now these are linear factors with complex coefficients. And these are linear factors with real coefficients. And that would be our answer for part B. So when it comes to problems like these, you can really imagine it that you're finding the complete factorization of p of x. It's just that your answer for A is everything that you do until you have to take a square root of a negative number. And then part B is just going the rest of the way. So it's kind of like you're doing one complete factorization of the polynomial, and your answer for A is just like 75% of the way there, and your answer for B is 100% of the way there. So, all right, that wraps up our work for example 4 then. All right, so wrapping up example 4, then that wraps up section 3.5. So in 3.5, we covered the fundamental theorem of algebra, complete factorization, zeros and their multiplicities, complex zeros that come in conjugate pairs, and linear and quadratic factors.